But one of the great things that I think from this forum already to start it is, I don't think I've ever been to one of these things with AHS where we had to turn people away. We had to turn a bunch of people away. You know, we filled up pretty quickly right at the end, and but I think it's exciting because all the things that a lot of us have been working our entire careers are now the exciting technologies that we're moving forward with, not only in DoD but in the nation, internationally. This is really an exciting time for the VTOL business and for us who have been working these issues for a long time. So with that, I shook some hands. If I didn't get a chance to shake your hand, watch out, I'm going to get you during a break or something like that. So we'll start out by introducing Graham Drozeski. He's working at DARPA in TTO. Currently working DARPA turn and alias programs, as well as some other vertical takeoff and landing aircraft, guidance systems, control and autonomy, distributed operations, man-to-man teaming, human interface, fault-tolerant systems, rotorcraft survivability. Kind of sounds like my portfolio, Greg. But prior to getting to DARPA, Graham also served as a chief engineer down at Aurora, where he developed advanced VTOL rotorcraft and VTOL and fixed wing. Autonomy systems, transformational technologies, and operations for ship-based unmanned systems. He also spent some time as the flight technologies point of contact for KARM aircraft, where he served as the lead for military rotorcraft developments. But the most important thing, he was a U.S. Army aviator. So got a PhD and a master's degree from Georgia Tech and a bachelor's from Notre Dame. Graham.
Thanks, Bill. Sounds like it's working. Bill introduced me at a specialist meeting something like 15 years ago. Army aviation, the VTOL community as a whole was in a very different place then. Comanche had just been canceled, DARPA followed by canceling UCAR. The V-22 was getting over the Marana incident, but it was still a very different time. The Army was backing away and saying, we want to go back and double down on our old platforms from the 50s, 60s, 70s. Now, today, where we are, it's a completely different field. Where we've come in the 10, 15 years since then, from starting all these platforms, whether it's V-280, S-97, all the new things that are coming up in the commercial industry. That's what I want to talk about today. And I want to talk about synergies between those two spheres of development and how we can push forward as we move ahead. Okay, so that's where I went through this slide, and here's sort of a quick look at two different but similar mission sets. And here we are. Right here in San Francisco, and later this week I have to have a meeting down in San Jose, and I wish I had one of these things that got me here in 15 minutes. But I'm going to make that drive. I'm going to talk a lot about both industries, and unfortunately most of the stuff that I talk about on this use case in the right is rooted in the Uber Elevate report. That's only because the Uber Elevate report's in the public domain and provides lots of good data. So please don't say that I'm advocating Uber above any other implementations in this realm, but certainly amazing things that are being accomplished here. I'd also say amazing things are being accomplished here. And I centered these range rings in Fort Campbell for no reason in particular. I didn't want to put them overseas, but look at the ranges now. We have lots of programs moving out to. With the Marine Corps version of Capability Set 3 and Future Vertical Lift, 450-mile radius. Turn, one of my aircraft, is a 600-mile radius. And then I put Ares on there, but there's others with the MUX coming. So the radiuses of action for the military aircraft are going places that above and beyond where we were in V-22 and incredible leaps above where we are with conventional helicopters. I put four sort of driving capability sets for each use case, and I'd say there's a yin and yang to both of them that goes to the commercial case and the military case. Expeditionary, certainly, I mean, we're operating without any infrastructure. We're operating in places that are remote, dusty, rugged, hard to get to, and a long way away. But as you talk to people in the military more and more, you'll notice that they're starting to talk about urban. How do we fight in that urban environment? And what do the aircraft that operate in that urban environment look like? So you are starting to see more urban coming into the military side. And I'd say that we're starting to see, or we'd like to see, perhaps more expeditionary look at this case. So instead of operating from instrument-certified heliports, a select number of those, you really want to go directly to the point of need, and you don't want to have to put all the infrastructure investment into that point of need that you put into an instrument-rated heliport that goes through all the certifications we do right now. Certainly efficiency metrics are different. When I talk about the commercial side, pennies per mile, pennies per passenger mile, that is more than just the fuel, right? That's the infrastructure, that's the pilot, that's the amortization of the aircraft. It's the whole business case. On the military side, I think much more in the pounds of fuel, but maybe that's a little bit short-sighted. Maybe we should talk about costs there. Capacity. On capacity on the commercial side, I think it's passengers per aircraft per day. Maybe it's ton miles per aircraft per day in capacity on the military side. But certainly there's equal yin and yang looks at both of those. I'm going to talk briefly for 20 minutes, and I'm going to have a slide or two on air vehicle developments and autonomy. And I would say autonomy is critically important here. The air vehicle stuff that we're seeing, we are having aircraft that can perform like this, and I think that we could say we could have aircraft perform like that even using not fossil fuels. But the autonomy to enable us to operate routinely with the number of nines, 9 nines, 7 nines that we need to operate reliably in those environments, that's a huge hurdle, and it's a huge hurdle on both sides. This is a look, probably my only chart on the air vehicle side of it. And if you look up here at the upper left, this is a payload range chart, but I laid contours of payload range onto the chart. And so payload range, it has the same units as energy. It's not really energy because your energy goes with the whole weight of the aircraft, the whole efficiency, lift over drag, all those things come in. But it does give you a sort of indicator of the energy required to accomplish a certain mission. And you look here from the Black Hawk to the Future Vertical Lift, there's a 4 times increase in payload range. Now, of course, Future Vertical Lift are going to be probably bigger aircraft than the Black Hawk. They're also going to be faster and have all sorts of other features that we don't have in terms of survivability and other capabilities that get built in doing an aircraft so many years later. But there is a big leap there. And there's a big leap in efficiency as well as a big leap in capability in terms of payload range. In this realm, sort of above the 500, there's multiple military developments. You take the Future Vertical Lift ICD, and you've got all those categories of payload range. There's other platforms in here. There's Ares, Turn. Turn, of course, is has to loiter out there, so that's a little bit different case. I didn't mix in the loitering with my payload, time on station with my payload range. But lots of military stuff up here, and I've sort of grouped them all into efficient, and efficient meaning a step beyond effective lift over drag of 4. And then you see developments down in this lower right side, and that is a generic 4-passenger on-demand mobility aircraft, and there's lots of other things that sort of come in, maybe a 2-passenger, maybe there's Eagle Eye over here, but there's been things around this realm. In this bound in here, this box I draw on the PowerPoint, we've got a lot of traditional helicopters, small helicopters in that realm, but we haven't had a lot of what I'd call efficient VTOL reaching down, so tilt rotors, tilt wings, those kinds of things getting smaller and smaller and coming in from this direction, and then maybe the on-demand mobility stuff moving up into here. And I think that's a fertile ground that I would like to explore. I think that cargo in particular may reside up in here. If we're going to operate in cities, and I'm assuming that we found a way to get to the city, but now I just need to operate within the radiuses that city, that urban megacity comprises, maybe you no longer need to go 500 nautical miles to get there. Maybe you have a shorter time on station and presence and being able to operate in and amongst those buildings reliably. Maybe that's what you're after. Of course, this is a lot more complicated than this plot, and I put some simple range equations that maybe get at the differences between the platforms and the commonality and tech pushes between the platforms. One thing I'd like to draw specific attention to is what I've defined here as percent weight load, percent of useful, actually percent not useful load is percent of the weight you're landing at. and some subtle things there, and they're going to tie into when I talk to autonomy in a few minutes. So what goes in here? Weight of my operating weight empty, and percent weight of my operating weight empty. And of course, that includes the crew on board, right? So the crew and all the unexpended fuels and all those other things go into my operating weight empty. And when you get into these classes, 500 pounds of crew starts to mean a lot. And so if you have the autonomy that can go from 2 to 1, 1 to 0, et cetera, you're buying yourself lots of space in terms of the aircraft design, capacity, how much capability you get out of a given size of aircraft, or you're buying yourself something in terms of just additional energy you're pouring onto an existing airframe. Okay, autonomy. There was a lot of talk about aircraft survivability 2009, 2010 regarding the conflicts we had in Iraq, in Afghanistan, and other countries. And I have no new results here to show you, but I put pie charts together to sort of emphasize some of those critical points. Upper left, and this includes in hostile environment, non-combat and combat, hostile, non-hostile, all those environments aggregated together. 79% of the fatalities, according to this report, and it's a well received report by the guys at IDA, 79% of those had human contribution to the fatality. 79%. So we have got to find a way to pull that down, not just from a safety reliability point, but from a survivability and mission effectiveness point in the military. And controlled flight into terrain is something I always bang the drum on. That is a large contributor. When you're at speed and you hit the terrain, the number of casualties on board is catastrophic. That being said, as we start and look at use of these aircraft in routine usage in CONUS, in the national airspace, these sorts of fractions of non-human to human are also not acceptable. Not acceptable, maybe the percentages is acceptable, but we have got to dramatically reduce mishaps and fatalities to get wider acceptance of VTOL. And so either way you're going, I'd say all the civil stuff goes through this problem. It's a little different problem when you're not getting shot at, but it's still a problem. And then economics. On the civil side, and this is based again on the Uber Elevate report, if you tear apart the dollar figures in their back chapters of that document, you see that the cost of operating these on-demand mobility aircraft 3 times as much goes to the crew as goes to the actual fuel. Now this is assuming that they're getting power off the grid at so many pennies per kilowatt hour, but still, reducing the crew operations from a single pilot down to a pilot at each receiving station, at each heliport, is a huge step, economic motivator for the autonomy. Now, airports, when you go to an airport, they are good. You know, they just made the release. It was something like 7 years since there was a U.S. air carrier with a mishap. That's the direction we want to go. They have a much easier place to operate than we do. They have these huge airports that are monitored. There's redundancy. You have fuel on board to get to other airports if you have some sort of either mishap on the aircraft or with the ground equipment. So it's a different environment, but we need to head that direction to get the routine operations. And oh, by the way, if we're going to be doing short hops in small aircraft, we need to put all-weather capability, but we need to look at how can we absorb all the burden that goes with flying IFR. We want to fly IMC. We don't want to have to fly IFR, at least under existing IFR. With a 30-minute reserve, but that's not the half of it, right? It's 30 minutes, but if you need an alternate, you got to have all the fuel to get to your alternate. An approach takes like 15 minutes instead of taking 2 minutes because you don't just shoot right in there. You got to shoot the whole procedure. So how does that become more efficient? And we reduce the energy burden of IFR flight on small aircraft. I've hit this a couple times about going from 2 pilots to 1 pilot to 0 pilots, and I'll talk a little bit about where some military programs are heading that direction. I think that there's lots of headway being made, including the last one, which I think has tie-ins both on the military and the commercial side. Okay. So in this era, I was working on things like this. I'll be honest, and I was briefing at AHS, for that matter, on things like this. So the community really works, and it's really been foundational for me. But at that point, we thought that we were flying unmanned, man-rated helicopters like this one. And I thought, being a former Army helicopter, but this stuff's going to be there in 2 years. This stuff's going to be there in 3 years. We are at the cusp of a revolution. Well, now we're 2017, and we made incredible progress. What we did here, although this architecture may look very similar to a current day architecture, to what's being done in the ALIAS and AHS programs, is huge steps. But to really come to bear and to affect how we operate, we need to find ways to get this stuff into the field and beyond the way it was in the field in just a KMAX, which was great. It was sort of foundational for us, but we need routine operation in the field in man-rated helicopters. And how do we get there? I am working in this, and I think that I have a vision for what we'd like to, the throughput we'd like to have, but all the ideas you have in terms of ways to get certificated autonomy in the field, I'm eager to hear. I think we want to be able to leverage all the great things that people are doing in terms of computing, in terms of non-deterministic algorithms, in terms of emerging AI. We don't want to cut that off the table because of certain certification implications. So we need to be able to have access to all those emerging and rapidly emerging things. On the computing side, we got to be able to use the fastest computers. We got to be able to do multi-core and multi-threading and GPUs, all those things. We shouldn't be leaving those off the table just because of certification. So we want processes that enable using these things, but oh, by the way, we need a means of compliance to get there. We need to think about it from the start. So don't just think about an aircraft, designing this efficient aircraft, and then putting autonomy on afterwards. You got to start thinking about that from the beginning, thinking about the implications of what are the speeds, what are the sensor horizons, what is the redundancy in the actuators, redundancy in the sensors, redundancy in the computing, all those things. And I'm not saying you need all those things. I'm saying you need to think about those things early in your design cycle, right? Are we confined by the RMP type of notions of operation that you see in the civil airlines? And finally, I guess there's two slippery slopes in this discussion that I'd like to emphasize. One is don't fall into the regime of I proved it works, and therefore, I did this one-off demonstrator, shortcutting all these things here, and it works, and therefore someone's going to take it. I think we're very much getting to that realization that we can do the things we want with the algorithms and the autonomy, but we need to pull them through the certification. So stop thinking about doing a one-off demonstration. Start thinking about how we build something that can be applied to a fleet. The second thing I'd say is don't do it in the stovepipe one-up method where I can't come back later and say I want to add a new sensor, a new algorithm. I want a new sensor, a new algorithm from another vendor. I want this open so I can pull all this in and not have to redesign all my flight code, recertify all my flight code just because we came up with, there was a Tesla story. The Tesla saw a kangaroo and it didn't know what to do with the kangaroo in Australia because that wasn't something in the database. So how do we bowl that in without rewriting our flight control laws? We need a way to do that. That is the second slippery slope I'd mention. Okay, this is a VTOL platform discussion, and I've been involved with a few of these developments, and so I decided I would talk a little bit about some heartburn, some scar tissue that I have in those development programs. And I'd say that the sooner you can model the interior of the conversion corridor, not at the hover and at the fixed wing, but in the middle, the sooner that you can model that, the better off you are. It's very easy to approach a program like this and say, oh, it's going to be somewhere in there, but the devil's in the details. And I think there's been program after program that have come to the realization that I wish I had a better model sooner in the development. And so I'd say think about that. I'd say all aircraft, even the coaxes that Sikorsky is pursuing, they have some sort of a transition from a helicopter type regime to a highly efficient greater than LDE of 4 type regime. I'd say that when you write the requirements, if you're writing the requirements for your conversion corridor, think about everything you need out of it. You know, there was Ashish under his X-plane program said that you need to have trim at all airspeeds, and that is a good way to define it. But some aircraft need more than trim at all airspeeds. The tilt rotors, they need to shoot descending approaches, which means you need to be able to trim with a negative gamma. And so that's something. We had on the Joint Heavy Lift program, we had a CT on Sigma requirement at 80 knots. So there's requirements like this that come in, but you need to understand those so that you know what you need. And oh, by the way, there's failures that can occur at any place, right? I can fail a tilt actuator, I can fail any of these things, and you need to think about how am I coming back from that? Is it a rolling landing? I'd encourage you to think about rolling landings for emergency procedures, maybe for takeoffs and landings for these aircraft that are severely constrained in the amount of energy, and as disk loadings and advanced VTOL may put a larger fraction of that energy into the takeoff and landing event. 50 or 100 feet of rolling distance could make a big difference in the amount of energy that goes into that takeoff and landing event. And so just pay attention to that. This is of course, XV-15. Over here's the X-22, which was a ducted fan and had this level sort of conversion. I don't want to get into the physics of the X-22, but I would say it's interesting to note that it went from 160 knots to 0 knots in 28.4 seconds. So those ducts can create a lot of drag, a lot of momentum drag. You're slowing at 5 or 6 knots a second there over the average descent or deceleration, and that's what the flight manual's telling you to do. That's not the, I'm standing it on the tail and kicking the tail out to the right. So this is my closing slide, and I'd like to look again at the pictures on the right. These are all military programs that either recently flew or are soon to fly. I mean, if you look at that where we were in 2004 and Comanche was canceled, we're in an incredible place. We're going to revolutionize what the military can do in terms of vertical takeoff and landing in the near frame. And all these things are happening even faster. And so it's an incredible time. It's an incredible opportunity to revitalize the military community that's sort of driven VTOL, the revitalization that we can get from the community that's really home here in San Francisco. It's a huge opportunity. And to drive new paradigms in certification, to drive new ways of thinking about the aircraft, to drive faster development cycles, and new ways of thinking about pulling software into the platforms. All those things are opportunities for us, as well as the people, because this industry all comes back to people and getting people jazzed up, getting the young software engineer, the young aerospace engineer jazzed up to come want to work in this field. It's great. So I'm excited, and with that, I'll turn it over to questions.
So with that introduction, probably need to start first by making sure you're not losing faith in Barry, who invited the fighter pilot to come talk to a bunch of professionals in the rotary wing business. Thanks for the opportunity to do that. Between Barry and Mike, wanted to have me talk a little bit about requirements, being in my current job on the joint staff, and then also test, because clearly with my one flight in the Dolphin there, I am the world's renowned expert on rotary wing flight tests. So sit back, and I'm sure you're going to learn some things. Kind of thinking about some of the existential threats like Barry has with his job right now, maybe step back and look at what are some of the key questions of really why are we here today? And in doing that, looking around at a lot of the literature, we talk about the height curves on certain things, and certainly eVTOL is quickly going up the height curve. And so in doing that, kind of, with the humility of a fighter pilot, as everyone knows, looking at what are we really trying to accomplish here? And it seems like a pretty humble pursuit, trying to revolutionize transportation for the world. So why not? It seems like a phenomenal effort. And so before we really start looking at that, I thought it'd be good to look back just a little bit at some of the other revolutions in transportation. So we'll start here with a couple of my colleagues from the Pentagon working to the right. They're super busy, and when they get focused on a task, they stay highly, highly focused, don't want to get distracted by things. Fortunately, in the past, eventually these great innovators are able to get some of these technologies across to make amazing things like you see on the left there. So revolution and impact with somehow or another the F-16 Great Pyramid was the first thing that popped up on Google. Not sure how that happened. Eventually, further revolutions in transportation started to go green and take wind energy and use that to start moving us across continents, revolutionizing transportation, again, resulting in the amazing revolution of new worlds that we found. This revolution eventually started to heat up a bit. If we start at the bottom, with the steam engine helping push along the Industrial Revolution, the vehicles coupled with the Eisenhower interstate system that allowed us to have some social revolution in the United States, and then eventually aviation. And certainly I think while the internet and the ability to travel and ship a lot of things across sea were important, few could state just the value of being able to connect people around the world and the globalization that resulted from revolutions in aviation. And so there's been discussion of that we're in this third revolution of aviation. Interestingly, one of the individuals that suggested that was currently working at a company in Toulouse, France. I'm not sure how he didn't recognize the first one, given the French can't let you say the word Wright brother without talking about les frères Montgolfier. So starting with the hot air and the hot air balloons, eventually going into reciprocating engines, and then to jet engines, we kind of see this transformation of revolutions in transportation. Interesting, as you look across these different revolutions, there's some things in common, that there's also been an important requirement to invest in infrastructure with the railways, the roadways, and eventually the runways. And so as we get to this point of the potential revolutions, you're going to hear me echo many of the things that Graham said. We try to, across the Department of Defense, we coordinate very well, as I'm sure all of you know. That now, as we start to move into eVTOL, is it possible to get to a point of getting beyond the hot air here in transportation? Is it possible to get to a point where we use autonomy to the point that everyone can be a pilot using VTOL? So that's, in general, when we look at why we're here, I think there is potential for this to be a revolution. Besides this concept of revolution, another important thing I'd like for you to get out of this talk, a little technique of how you know you're at dinner with a fighter pilot. And you usually know that about halfway through dinner, the pilot says, well, that's enough about me, let's talk about flying. And so let's get back to me for just a little bit. Why am I here? That's the important part. If indeed there is a revolution in transportation that's going to allow us to accelerate movement of goods around the world, certainly in my current responsibility in requirements and capabilities development, the Department of Defense moves a lot of things around. And if there's ways of doing that at a lower cost, if there's ways of doing that with a reduced loss of human life, certainly we have a responsibility to do that. If you look at the amount that was spent on MRAPs, some $50 billion in trying to reduce IEDs. Just recently, there was a Distinguished Flying Cross for a C-130 crew that dropped goods into folks on the ground. If there's ways of doing that at a lower cost, a lower risk to human life, then certainly do that. And so looking at this first from a cost perspective, certainly cost to human life, but additionally cost, looking at procurement costs normalized to dollars per 100 pound, and then operations and maintenance cost. Again, open source, anyone that's done much with cost data certainly knows never trust the numbers. But at a first hack, what do you see here? In this red zone, so each of these represents a particular aircraft. In that red zone, what you find all of our recent programs, typically high procurement cost, high operations cost. The other thing you'll find looking at this is among DoD programs, you're not going to find any VTOL programs down in that green zone there. Obviously, some benefit in potentially looking at distributed operations with that reduced operations and procurement cost. Besides the cost piece, there's also the schedule. Besides bad hairdos and peculiar outfits in the 1970s. There's some other strange things that happened along our development timeline. And you see that the aircraft that we've been developing in DoD since the mid-70s, the development years to completion has increased significantly. We just aren't taking products to the field, to the warfighter as quick as we used to. And so there's a question, in this revolution in transportation, is it possible to follow more of a commercial model? As Graham mentioned, DoD one of the first to bring UAVs, and you might notice that those were some anomalies over the last few years, that we were able to get to those a little bit quicker than some of the other products. And so fundamentally, from a DoD perspective, from a requirements perspective, we, as Eisenhower said, logistics is fundamental to our warfighting capability. And are there ways of reducing human cost, reducing the monetary cost, and increasing the schedule to be able to bring these products to field quicker? So that made us think, what are the opportunities that are out there? And at this current point, not necessarily hard requirements. We've got MUX is currently in my portfolio, but among the Joint Staff started looking at several of these problems. Why do we have some of these problems out there? And is there a capability set that could potentially meet several requirements, all with a new type of platform? It's not necessarily a helicopter, it didn't seem like, not necessarily an aircraft in particular in a traditional sense, but something that could meet many requirements with a bus-light capability that, and the term we came up with was this Omni requirements bus idea of being able to meet many requirements by being able to attach new things to these new, smaller pieces of equipment and be able to realize then some of the cost and schedule savings. When we looked at that, so the advantages of the digital propulsion, one of the other cost factors is the ability to get logistics from a sustainability perspective, reducing the multiple consecutive miracles that somebody like me looks at a rotary aircraft and stands in amazement that you can actually beat Newton down to the point that those things fly. But could we increase this, make those simpler and provide the capability at a lower cost to the field? The other piece, going back to my good friends here in the Pentagon, are there ways of increasing our technology absorption? Many of our programs, besides the initial schedule, there's also this problem that when we want to go do an upgrade, F-35, great example, the challenge of getting new technologies on there. Oftentimes we find ourselves that we'll buy an axle that's got a square peg on it only to find that everyone is building only round holes. And this square peg and a round hole problem frequently results in delay and results in additional costs sent to the taxpayer. So if indeed there is this opportunity, this revolution potential in aviation, how do we get there quickly? And I think fundamentally it requires some trust. And again, echoing some of the things that Graham had mentioned in terms of being able to distribute some of the risk across this triple helix idea between academia, industry, and government. There's different risk profiles that we can take, and we can share risk differently. And so what are the opportunities for that collaboration, to share that risk, to find the right human capital in these different areas, so that if we really want to get to an enduring speed of development on these capabilities, there has to be some degree of enduring trust among the community. And I think that starts with test. Looking at the test, right, a profile of the probability of failure and impact of failure. As we look at that, there's a lot of different ways of approaching that. Obviously, if I sit on my couch and eat potato chips all day, low risk of me dying in a aircraft accident. But there is a very high risk that I'm going to just sit there and get fat. And I think to some degree, we, in some of our risk profiles, might not be taking enough risk. But what I'd suggest is that by looking at culture, approaching the speed of development at the right pace, improving collaboration between different organizations, we can eventually increase the trust level that allows us to take a lower risk profile and still stay at an accelerated. Looking at test, fundamentally test is managing that risk. Starting with the requirements, some of the bench testing, subscale testing, eventually moving across into the prototype flights, and in this case now starting to look at how we approach autonomy and build trust in that autonomy from the pre-acquisition stage in laboratories moving into ranges, and then on into the actual operational environment. Again, from echoing Graham's remarks, we can't just go fly one prototype and say that's good. It does, but getting those prototypes out there and learning quickly, critically important. So as we begin looking at this, first and foremost, from flight test, what are kind of the three core things that they teach? Performance, flying qualities, and systems. And there has to be good test measures across those things, agreed test measures, so that you know that you're getting the right data, so that if there is a deficiency, that there's a shared understanding of what that deficiency is, and then a potential of a redesign, so that from a validation perspective, the aircraft is actually meeting the requirement, and from a verification perspective, did I look back at the right thing? And so, for example, a Cooper-Harper rating. I think there's some challenges as we move into this new world. We don't necessarily know what the flying qualities might look like on this. We don't necessarily know what it means to be a pilot in these scenarios. From looking at test requirements and designs to the beginning of this, as many of you know, a significant amount of the leverage that you have in management comes at the very beginning of that cycle, the concept development. And so what are the things that you can do by incorporating a test team early into that, designing to some degree for test, and then keeping that test team engaged? What is test doing? So if I were to imagine some way of flowing a physics-based design through a value function and a cost function, there's some uncertainty around that at the beginning. The purpose of flight test is to reduce that uncertainty. Oftentimes when you're reducing that uncertainty through flight test, there's some redesign there. And so having closely coupled test teams with the development teams in order to iterate quickly and update those designs. Another piece is this concept of slowing down sometimes to speed up. So if you look at me closely, besides doing flight tests, you'll see many scars. The Air Force at one point decided it was important for me to go get some program management experience, and spent a couple of years dealing with intellectual property rights on cyber resiliency modifications. What I learned from that is it seems to be, I know it's very hard to do that after the fact of going and trying to fix embedded systems. And so what I would suggest is if we are going to start developing these systems that are highly hardware and software dependent, making sure that some of that is baked in from the beginning, starting to look from the outset, what are the roles of DO-178? How can some of that be done from the beginning, still moving quickly with a prototype, but understanding that eventually if you're going to get to a certification level to fly in the national airspace, whether I'm going to the battlefield or to the soccer field with this new type of technology, there's a need to make sure that there is trust in those systems, especially if we're moving towards more autonomy and more dependency on them. Additionally, slowing down to speed up, are there ways of taking, so when I was flight test commander at Holloman, we would go fly things on old airplanes, new things on old airplanes. Can we use flying test beds to accelerate some things? Would you rather fly a fully integrated quicker? Yeah, maybe so, but the lessons that you can learn by distributing that test, again, distributing some of the risk, you might actually speed yourself up. Last, from pilots and autonomy perspective. So, being an F-16 pilot, my brother flies B-2s. Both of those airplanes, we grew up flying ultralights on a family farm, and that was very much stick and rudder capability. Today, anytime we're getting in those planes, we're basically a voting member. And so eventually, there's been some development that we have been trusting more and more computer intervention in what we're doing. Those airplanes wouldn't fly without that. The F-35 first missile shot there, sending an AMRAAM off a significant amount of trust in a missile that is a launch and leave. And so how do we go and leverage some of that in order to build that trust? One thing we do at the test pilot school when I was an instructor there with the F-16, while it was a flight control system that was highly augmented with computer system, it would put limits on the angle of attack. And in theory, it should only go to 25 degrees AOA. Now, Barry gave me authorization to shoot my watch down just one time on this. But when you're in, again, an operational environment, if you're doing air-to-air combat, you're not maneuvering in relationship to the ground, but in relationship to the other aircraft. Oftentimes, that's going to put you in a vertical situation at a low airspeed. So at the test pilot school, to build confidence, we would take new pilots, go fly vertical up to 40,000 feet until it ran out of airspace, speed, tail slide, and it would eventually go well beyond that 25 degrees to an unstable point and then stabilize at 60 degrees AOA, falling back towards the Earth, inverted, and later on, as in seeing this, there's an additional switch that they put in there, an MPO switch. And so, again, when this airplane first came out, not a lot of trust that the computer system could actually fly the airplane. But that trust was built, and eventually, with enough bananas, you were able to get us pilots to continue flying those types of planes. So, in closing, I think certainly a very strong case that can be made for we are in a revolution. I think huge potential benefits that can arise from this revolution, but in order to get there quickly, what are the things we can do in testing to get data quickly, to develop trust in the systems, to develop trust across those communities? And a final note, I think it's important to really think about some of the culture. Having an opportunity to fly with several different countries, across several different types of airplanes, obviously the rotary wing, the hang gliding culture, my 12-year-old there trying that out. There are significant differences in cultures. I think, interestingly, here with the software and with a lot of the folks that are getting involved in this, integrating the Silicon Valley culture with a military culture, with a civil aviation culture, how do we do that in a way that accelerates trust? How do we do that in a way that encourages, I spend a lot of time with some of the STEM programs and young kids. It's amazing how energized they are by seeing kind of this sci-fi opportunity that comes from eVTOL. And how do we bring them in quicker to in a community that develops trust, in a community that allows us to accelerate this capability and bring the fruits of the potential eVTOL revolution to the Department of Defense and across the world?
Thank you, sir.
Thank you. Thank you for inviting me here. This is a great honor. First of all, I want to congratulate all of you for your sustained service to VTOL and helicopter industry. What you're seeing now is the almost VTOL 2.0, and I think it's because of your sustained service and dedication and resilience that we are here and seeing the opportunity in the electric VTOL and hybrid VTOL space. So thank you for your great service to this community. Second is that Barry mentioned that we are at overcapacity. This is the first time it's happened, I think, and this is the first time they invited me to talk. There is no. This is a good example of causality and correlation. It's not limited. Might be there, yeah. So. But and the other good example is all three of the speakers, plenary speakers, have been wearing blue color trousers. So that's another causality and correlation example. But nonetheless, thank you for inviting me here. I'm here to talk about the airspace integration, and I want to thank the first speaker, Graham, on chart 6. He said, I will not go into physics, and I was relieved when he said that. And the second speaker for talking about the importance of logistics, which is what airspace integration is all about. So I'm here to talk about how we can enable large-scale operations in the airspace, heterogeneous vehicles, all kinds of different types of vehicles. And and there is a reason why people call me PK. You probably surmise that from my name. So here is our current national airspace system, and we have typically 50,000 operations per day, 5,000 to 7,000 at peak. This is what the current system looks like. And we have 25% aircraft get delayed. 75% of those 25% are due to weather. So that's what the current airspace system looks like. The three bottlenecks in the system are gates, runways, and workload of human being, primarily controllers and some pilots. But that's the characteristics of the current airspace system. And that's important as we move along and looking at enabling future vehicles. How do we actually make sure that we don't get bottlenecked by the same situations? Now, few years ago, we started working on this drone traffic management or small unmanned aircraft system traffic management program research project, little project we started. And it wasn't fashionable till Amazon came up with their video, and then people, so what is that little thing that PK you're working on? All of a sudden it took off, so to speak. And the idea here is to enable large-scale UAS operations in the airspace. If you look at the forecast, FAA's forecast says that by 2020, 7 million these small vehicles will take basically into operations, and 2.6 million will be commercial. So if you compare that with the current aircraft that operate, and you quickly realize that we don't want to be definitely get bottlenecked by the current limitations or the barriers of the system. Then you move forward, as we are talking here, vertical takeoff and landing, new generation of vertical takeoff and landing vehicles are coming up. This is a chart that I took from my good friend from NASA Langley, Ken Goodrich. And the idea here is to enable beyond drones. We want to enable these vehicles flying everywhere. Some people like call flying taxis and such, and others don't like that characterization. Some like to just call it eVTOL. But the idea is to basically enable 1 to 5 passenger on cargo industry in the urban airspace or suburban airspace. Well, then you move forward and say, okay, what will happen? You really then start to postulate that the drones, the helicopters, conventional helicopters, and the electric VTOLs or hybrid VTOLs will all be operating in the same airspace. And quickly you realize that scale is going to be tremendous. Even though we don't have reliable forecast yet or when this will happen, but the idea is to conduct research, development, testing to enable this kind of environment so that we can safely manage all these operations and give you the maximum value through air. That's sort of what we are working on. You go even further and say, okay, what would that mean for all airspace users? So you saw the picture of the small unmanned aircraft system. You saw the urban air mobility. Then currently we have subsonic transport aviation that's very well matured and is growing as well. Then we have high altitude upper airspace operations coming up with Google Loon and Facebook Aquila and AeroVironment and a whole bunch of DoD operations. Then you have supersonic, subsonic, and then commercial space operations. That is also now vertical takeoff and landing. I don't know how much we characterize that in this group, but commercial space operations, they all want access, they all want efficiency, they all want safety, and they all want scalability. And that's the problem that I'm really passionate about. So let me skip one chart and get back to this, the architecture chart. But when we talk about urban air mobility, airspace integration, what are the main principles? The fundamental principle, looking at the bottlenecks and the lessons learned of history of air traffic management, which started because of the collision over Grand Canyon in 1956. As you know, FAA started in 1958. NASA also started in 1958. But fundamentally, we want to provide no burden on the current air traffic management system. So that's one principle. Second, it has to be cooperative and interoperable with other users. So we can accommodate multiple heterogeneous users. It's got to be performance-based and risk-based so that your characterization of your performance allows you to fly based on where that performance is most suitable. If you're flying in very tight corridors, you need a different type of equipage, and if you're flying over ocean or low-risk areas, maybe your uncertainty can be higher. Efficiency is some other things that we always want in the system, as you heard from our second speaker, the logistics. Wars have been lost because of the lack of proper logistics and efficient logistics. Safety, our first speaker talked about that, the need for safety of all types of operation, particularly as we move towards autonomous operations. And for you and me, sustainability of these operations, scalability and affordability becomes very, very important so that common people like me who are civil servants can also afford these operations and air taxis. Even though I live in Silicon Valley and I have lots of rich people, rich friends, and I jokingly say, oh, we tripled our profits and we did this, and we say, yeah, what are you working on? I'm working on trying to triple the capacity of the airspace. And they lose quickly interest. So that's not what the tripling effect means for them. But joking aside, That's how we get passionate about. So let's get back to the architecture. So looking at all these operations, what are different ways we can accommodate these operations without burdening the air traffic controller system? So you see here, this is the flight information management system, which is the FAA side of the house. Then you can see that the operators, the US or the urban air mobility operators, and then we characterize another term called USS, or urban air service supplier, or US service suppliers. So this three-way of division of labor and roles responsibility allows us to basically change the paradigm in the current system, which is everything goes through the air traffic control system, and every change to your trajectory or your flight has to be approved by ATC. So every speed change, altitude change, heading change has to be approved there. Now we do that opposite of that, which is to tell us where not to go, and we will figure out how to go there. But in order to get there, we need complete digitization and connectivity, and we'll talk a little bit more about that. So the idea is that the flight management information system will tell you the constraints and any directives that happen to be in the airspace. Stay away from this because there's an airport, or there is a firefighting activity going on, or president is visiting. And then you as an operator, either yourself or using third-party services, create your plans and share your plan and interact with other operators. So there is a inter-USS coordination in terms of figuring out how to stay away from each other. So the responsibility then shifts slowly towards the operators. You also need lots of data about weather, terrain, and surveillance and performance. That also opens up door for basically third-party services. So if you look at this architecture carefully, you see lots of opportunity for service suppliers to provide these services. And the interaction between the operators or the third-party service suppliers who are using or who are being used by the operators only tell FAA systems any deviations or operations that are getting out of basically bounds, or things that FAA needs to know. Otherwise, that airspace gets managed. And largely this construct, we start off in the uncontrolled airspace, Class G airspace, as starting point, and slowly evolve to that, to upper Class E, and then other locations where we can actually start to move towards service-oriented architecture. So this is the basic idea of changing the paradigm of the current operations to enable the scale that we are referring to of these new vehicles and new air. The fundamental premise here is, mantra here is the flexibility where possible and structure where necessary. As I mentioned, in the current ATM system, the structure that's guaranteed and the flexibility is an exception, so we flip the model completely. But in order to get there, we need lots of connectivity and information exchange. Okay, so you see the layering of this system. You see that we had to guarantee separation, then it goes, you had to then guarantee some spacing to stay away from each other. Some scheduling then becomes important, because if everybody is trying to go to the same vertipads or locations that are close to each other, how do you schedule them so that we don't land up bunching together? Then demand capacity coordination happens. Now today's world, we do demand capacity coordination primarily for workload and runway and gates. And as you go towards VTOL and helicopters and other operations, you had to worry about demand capacity for noise as well as spectrum availability and volume of the vehicle. So there are subtleties that start to emerge in terms of capacity and demand. You can only accommodate certain vehicles because of noise constraints and such. This is where your research on aeroacoustics, noise modeling, that my good friend here, Susan, is championing, becomes really, really important. Then we talk about these services are cloud-based, so logistics is all basically making things efficient, and we want to get these services very efficient, but they don't need to be centralized. They can be in the cloud, and you can actually continuously get the information about the weather. One of the requirements for these vehicles to operate safely is thorough understanding of the weather, particularly the winds and the gusts at the lower altitude airspace, tracking these vehicles current systems may not be able to track them very efficiently to the scale that we are talking about, or it might overwhelm the current system for tracking. So we need to develop our own ways of tracking these vehicles, and in general, creating trajectories and changing trajectories, and then overall airspace and traffic constraints as to where those vehicles are able to go and where they can't go. But in order to do that, we have the basically structure, the connectivity between the aircraft, the air mobility operations center, the support service suppliers that I mentioned in the last slide, the air navigation service provider, which is FAA in our case, and the demand that's generated by the users. So really, it's about connected system to enable the scalability that we are referring to. Here is another example of that connected system. As I mentioned, flexibility where possible and structure where necessary. So if you really are going between two vertipads and you've got a bunch of other vehicles going, and all of a sudden high winds show up, then you say, oh, I can't land there. What am I going to do? If you want to then go find a safe landing spot in a different vertipad, you also want to know that vertipad is not occupied. So that information about the availability of the resource becomes important. So this is why you need to have connections to these other systems. So the idea then is to basically understand all the constraints in the airspace and connect them through the cloud or other services, and then figure out what is the best way to get there. Now, if you look at the aircraft, and assume that it's autonomous aircraft because that's the only one that's affordable for people like me, because the pilot costs are not necessarily affordable. So then what do I do? So you need to have basically fully autonomous capability for takeoff and landing. That means last and first 100 feet becomes extremely important as you go close to the vertipad that you want to land. So all these pieces basically become extremely important in terms of operations center, doing trajectory planning and fleet management, scheduling, as well as the support services, the connections into the air navigation service provider and the aircraft. So now once we connect these services, we say, well, how do we go about there? The previous two speakers talked very nicely about the need for testing and then walking through that basically tight path to get to the acceptance. Well, obviously we are one of the safest industries, and we want to maintain that, so we're not going to willy-nilly go towards some architecture and processes and practices that are not proven. So we go through crawl, walk, run, and fly takeoff approach. So we start with this is the right opportunity for us from airspace perspective because the density is low. So we create some initial operational capability. For example, you can start off with helicopter routes. There are about 10 cities that already have chartered helicopter routes using today's procedures. We talked about that architecture that we leverage in the US traffic management, UTM. So entry into the controlled airspace can be done through the UTM system. One of the things we described in the UTM very well is the data exchanges among operators as to share the intent with each other, as well as the data exchange about the trajectory or the area of operation into the FAA system. So using the standardized protocols and the data exchanges, you can enter into the controlled airspace. FAA also has a program called LANS, Low Altitude Authorization and Notification Capability, that leverages the UTM data exchange protocols, that allows you to say which airspace is open and available for them to enter. And the users primarily start to take a responsibility for developing conflict-free trajectories through UTM. Because once you are in the UTM, you have idea of what are the constraints in the airspace and what else is happening, so you can create your trajectories and areas of operation to stay away from each other. And then you track your own operations, particularly important when you go beyond visual line of sight without a pilot. The idea there is that you have to guarantee that you are where you said you are going to be. Then as you go towards the medium density, which is the interim capability, user will start to create these conflict-free trajectories again through the UTM, but then also interact and interoperate and be cooperative by sharing intent with the heterogeneous vehicles, be drones, be helicopters, be general aviation and such, and then self-manage their operations. And as you go towards extremely high-density operations where the mature capabilities, fully autonomous planning, scheduling, operations, disruptions, particularly aviation is all about being able to manage disruptions and unexpected situations and contingencies, and those things had to happen autonomously or automatically, so to speak. At the same time, we need to be able to use multiple simultaneous takeoff and landings at a bunch of vertiports or vertipads inside one port, as well as number of ports that are nearby. So that remains still an interesting research issue as to how close I can put these vertipads to each other and a bunch of vertiports in the cluster. From the perspective of passengers, it's efficient to do that, but then from the perspective of operations, what is that space and among the trajectories based on uncertainty and a lot of other characterization of winds and impact on the vehicle performance. So let's see how we get to this path towards the scalability. So we all want scalability, of course safety, efficiency, but we want to get to the high density or high scale. Otherwise these operations don't pan out in terms of its affordability. So first is looking at the architecture, roles, responsibilities, and technology that will allow self-management as much as possible. So that's first. Second is air traffic control system will still have a role, but they will interact indirectly, as I mentioned, with changing the model. For understanding the constraints and directives and changes to the airspace is how the interaction could occur. The operator will still be responsible for plans, schedules to the plan, and through the UTM kind of a characterization. Tracking, you will track your own vehicles, either through wireless, satellite, ADS-B, a whole bunch of other systems, beacon-based or pseudo-lights that are connected through the UTM, so that you have fundamentally very good idea as to where you are. And if you deviate from that, you need to be able to inform, the UTM system informs other operators that there could be a conflict, a strategic conflict and such. You will also need, of course, detect and avert and other technologies if you want to be fully autonomous. And then air-ground cloud integration system is absolutely necessary, as we talked about in terms of scalability to maintain the safety and efficiency at the same time. Last first 100 feet is something that is going to be needed for every autonomous vehicle that will ensure that when they take off and land, there is no disturbance in their trajectory and the profile. And we talked about vertipad, need for vertipad design guidelines and operations for simultaneous multiple takeoffs and landing, which is the key. The idea here is to have this whole integrated air-ground cloud integrated operations and system that allows us to get there. Now, let's look at what this environment may look like in terms of UTM style cooperative environment. So the characteristics of that UTM style construct are cooperative, first of all. So you share with each other, intent sharing, data exchanges among operators, and those are very well defined when you exchange information, what kind of information you exchange, what format you exchange, what's the latency and such, and standardized application protocol interfaces, APIs, air-ground integrated architecture, service-oriented architecture so that we can leverage services from industry rather than only provided by ANSPs as happens today, and then role for third parties. So that allows us to do towards innovation in the airspace operations. So we start off with low altitude airspace operations class G where there are no services. So we also look at high altitude UTM upper airspace E. There are no services provided by ANSPs today. Space traffic management, another emerging need where that kind of operation characterization and self basically management is going to be key. And then slowly we get to the conventional manned aviation. Conventional manned aviation will take a long time to transfer towards the UTM style sort of operations, but nonetheless you can start off with some of the philosophies and service oriented architecture where perhaps you can start to look at surveillance and communication as a starting point for transferring that responsibility in the services oriented architecture. Now, as I mentioned, and this is the point that I keep harping in a sense, the connectivity is really key. To understand the resources at the infrastructure, availability of the vertipads and vertiports and landing spots, real time, as well as the vehicle characterization as to where they can go or cannot go, whether they can go through the tight corridors that certain locations require, the airspace constraints and operations, the weather aspects and the scheduling and spacing, and the fleet management. So you might have to consider where basically the fleet characterization is and the maintenance kind of hubs are. So you could, for example, you have a bird strike and you have 3 decisions to make on the vehicle. The vehicle is autonomous. Imagine that vehicle has to make a decision. Should I land now? Should I continue? Or should I go back to the home? Then the idea is to, okay, well, I want to land to the nearest spot. Let's say that's the decision the vehicle makes. Well, how much time do you have? You have 3 minutes, for example. Then say, okay, well, should I go to this vertipad? If that vertipad, I need to be assured that vertipad is open and there is not much congestion going on there. It just happens that vertipad is experiencing high winds. Well, then I need to be able to go to some other vertipad that's available and guaranteed for me to safely land. And I have enough, basically, energy to get there. So it really requires that you understand airspace constraints as well as availability of the resources so you can make these decisions autonomously. So when we talk about autonomy and certification of autonomy, these characterization becomes very, very important. Another is the reserve fuel characteristics. General aviation has a requirement 30 to 45 minutes depending on when you operate to carry reserve fuel. Well, if your electric VTOL flight is only 20 minutes, you're not going to have that 30-minute another reserve fuel. So how do I meet the intent of that characteristics or the need while making sure that safety is guaranteed? So you may say, along my trajectory, I always have a path landing spot in mind. If something changes, I will get there on time. And with my reserve battery, I will be able to get there. But in order to get there, I also need to be assured that that spot is open when I want it to be. So if that spot is taken, I need to know that right away so I can go to some other place. A good example of that Sully-Sullenberger event, if you actually look at all the transcripts and data exchanges that happened between pilot and control, there's a lot of information that went back and forth, and a decision was made by pilot, of course, but the information that came back and forth, and then he realized that I can only do this. So that kind of stuff, information exchange has to happen at a very rapid pace. And autonomy alone, my point is autonomy alone will not lead to the significant efficiency and ability to manage large-scale disturbance. So we only talked about one vehicle. What happens if you have 17 other vehicles along the way and then you need to get everybody out of the way so that you can go and land because you have an emergency situation. So the large-scale disturbance, again, requires that you have complete understanding and connectivity and to be able to manage these kind of operations in an efficient and safe manner. So in terms of research, how much time do I have? 1 minute? Okay. In terms of research, so this is actually a very exciting time for people like me and you, where we can actually start to look at how do we create scalable environment with en route as well as arrival departure operations, particularly focus on off-nominal. We'll talk a little bit about that. And then it's cooperative and interoperable operations. We're starting from a place where there are no services right now, so it is easy to look at the vision of this cooperative and interoperable operations. Designing vertipads, multiple vertipads in a cluster, and proximity to other vertiports and vertipads. Weather and tolerant operations, as I mentioned before, 75% of the delays are due to weather. What kind of characteristics about the wind we ought to know? And we have learned some important lessons in the small UAS. Some of these vehicles with low wing loading bounced around quite a bit. And that has implications on how close you let them fly on top of each other or next to each other. So weather becomes very, very important. Of course, electric VTOL, these vehicles are a little bit heavier than the 55-pound, but nonetheless, understanding of the impact of the weather and the wind is very, very critical. High winds, wind shear, updrafts, all the things we had to consider, the power depletion, bird strike, everything that we talked about, the previous speakers also, figuring out how we are going to manage off-nominal conditions and contingencies is where the acceptance will basically be key. So a lot of our research and you all, I encourage you all to focus on the contingency and off-nominal conditions and how we are going to be able to manage those. We talked, and then developing requirements on the airspace system. Don't have to put all burden on the vehicle. It can be air, ground, cloud integrated system. And then you also have to assume that in case of link loss, what would you do? But so the requirements need to be flushed out based on this research so that we can actually do this three-way integrated air-ground cloud infrastructure connected system. And we are all about innovation. This is Silicon Valley hub of innovation. You can't have a talk in Silicon Valley without talking innovation. So this is all about innovation. But at the same time, aviation is all about safety. So here we're trying to marry, we're trying to embrace the innovation in aviation. At the same time, we're respecting the safety tradition of the aviation that we are all come fond of. So thank you again for your great service to the community. We're looking forward to collaborating with many of you. And we have a lot of, at NASA, Susan's project, our project, and what Colin is working on, we have a lot of opportunities for you all to collaborate, and we look forward to working closely with you to make this next generation of eVTOL industry happen. Thank you.